Hello there, and welcome to the Boring Universe channel. Take a moment now to settle in wherever you are. Let your shoulders drop, soften your breathing, and allow yourself to sink into this quiet space we're about to explore together. Tonight, we're going on a slow journey through the cosmos, following the peaceful life of a single star, from its first gentle stirrings in a cloud of dust to its calm, fading billions of years from now. There's no rush here, no urgency, just the soft unfolding of light and time. Close your eyes if you wish, and imagine the deepest silence you've ever known. Now, imagine it deeper still. Out in space, far beyond the noise of our world, there exists a darkness so complete it feels like velvet against your skin. In this darkness, enormous clouds drift, clouds made not of water, but of the finest dust and the lightest gases, spread across distances your mind can barely hold. These are called nebulae, and they are the nurseries of stars. You could think of them as cosmic cradles, rocking gently in the void, where starlight is born from nothing but patience and gravity's tender pull. One such cloud drifts now in your mind's eye. It's wider than 100 solar systems placed side by side, yet so thin that if you could reach out and touch it, your hand would pass through almost nothing at all. The dust particles within it are separated by vast spaces, each one floating alone in the cold, turning slowly in the dark, like snowflakes that will never fall. For millions of years, this cloud simply exists. It doesn't know it will become a star. It has no purpose, no intention. It only drifts, breathes, expands, and contracts with the slowest rhythm imaginable. Slower than seasons, slower than the creep of continents across Earth's surface. If you could hear it, it would sound like the faintest whisper, a breath held for 1,000 centuries. But something begins to happen so gradually that even time itself seems to hold still. In one small region of the cloud, particles begin to gather. Not quickly, there's no rush in the universe. One particle drifts close to another, and gravity, that gentlest of forces, draws them together. They touch, they stay. Another particle joins them, then another. Over thousands of years, a clump begins to form, no larger than a room at first, then a building, then a mountain. This is how stars begin, not with fire or explosion, but with the quietest accumulation. Dust finding dust. Loneliness ending in the slowest embrace. The clump grows denser. As more material gathers, the center begins to press inward, compressed by the weight of everything above it. Imagine a snowball forming in your hands, except this snowball is made of hydrogen and helium, and it's growing for 10,000 years without stopping. In the heart of this gathering cloud, something warm begins to wake. Temperature rises degree by degree, not hot yet, just less cold. The pressure builds like a hand closing gently into a fist. The particles are closer now, bumping into each other more frequently, and with each collision, a tiny bit of energy releases as heat. The cloud begins to glow very faintly, a dim red ember in the cosmic dark, barely visible, like the last coal in a dying fire. But this coal is not dying. It's being born. You could watch this cloud for a human lifetime and see almost no change. The glow would remain constant, the collapse imperceptible. Stars are patient. They understand that beauty takes time, that light must be earned slowly through the persistent pull of gravity and the gathering of scattered things into wholeness. The cloud continues to shrink, pulling itself inward from every direction. As it does, it begins to spin, slowly at first, then faster, like a figure skater drawing in their arms. This spin flattens the cloud into a disk, a cosmic whirlpool of dust and gas rotating in the darkness. At the center of this disk, the clump, now grown to something truly massive, continues its patient compression. For another 100,000 years, the process continues. The center grows hotter, denser, brighter. The temperature climbs past 1,000 degrees, then 10,000, then 100,000. The pressure becomes immense, atoms pressed so close together that their natural desire to remain separate begins to fail. And then, in a moment that arrives after millions of years of preparation, something miraculous happens. Two hydrogen atoms, forced together by unimaginable pressure and heat, overcome their resistance and fuse. They become helium, and in that transformation, they release light, pure, clean, brilliant light. Not much at first, just a flicker. But then another pair fuses, and another. And within the span of a few thousand years, billions upon billions of fusions are happening every second in the core. The star ignites, not with a bang, but with a gentle brightening, like dawn arriving over still water. The light pushes outward, meeting the inward crush of gravity, and for the first time, the two forces find balance. The collapse stops. The star settles into its shape, round and radiant, a sphere of light floating in the darkness. Our star has been born. If you could be there in that moment, protected somehow from the impossible heat, you would see a soft yellow glow emerging from the chaos, steady and calm. The surrounding disk of dust begins to thin as the star's light pushes it away. Some of that dust might one day form planets, moons, asteroids, but that's another story. For now, all that matters is this: a star exists where before there was only scattered emptiness. The new star doesn't celebrate, it simply shines. It has found its purpose without seeking it, achieved its form without effort, just by being exactly what it is, responding to the gentle laws that shape all things. There's something deeply peaceful in this, the way a star needs no instruction manual, no guidance. It simply follows the quiet physics of existence and becomes light. In the core, hydrogen continues fusing into helium at a steady, sustainable rate. The star has enough fuel to continue this process for billions of years, so much time that it's hard to comprehend. If the star's lifetime were compressed into a single human day, its birth would have taken just the first few seconds. Now begins the long, peaceful afternoon of its existence. The star settles into a rhythm, a cosmic heartbeat. Every second, millions of tons of hydrogen transform into helium in its core. Every second, light floods outward from the center, taking thousands of years just to travel from the core to the surface, bumping into particles, being absorbed and re-emitted countless times, slowly working its way up through the layers, like a swimmer rising through water toward the air above. When that light finally emerges at the surface, it streams out into space in all directions, traveling freely now, moving at the fastest speed the universe allows. Some of it might one day fall on a planet, warm a stone, help a flower grow. Some will travel for billions of years through empty space, never touching anything at all. But the star doesn't worry about where its light goes. It just gives endlessly, without thought or expectation. The star exists now in what astronomers call the main sequence, the long, stable period of a star's life when everything is balanced, peaceful, predictable. This is not a dramatic time. There are no explosions, no sudden changes, just the steady work of fusion, the constant outpouring of light, day after day, year after year, millennium after millennium. Imagine the most consistent thing you know, the way the sun rises each morning, the way waves return to shore, the way your heart beats in your chest while you sleep. Now, stretch that consistency across billions of years. That's what a star's main sequence feels like. Pure, unwavering presence. The star has a surface temperature now settled around 10,000 degrees in some places, cooler in others. If you could see it up close, from a safe distance, of course, you'd notice it's not perfectly uniform. The surface moves, flows, churns gently, like honey warming in sunlight. These movements are called convection currents. Hot plasma rises from below, reaches the surface, cools slightly, and sinks back down, creating a slow, rolling motion across the star's face. If you watched for years, you'd see patterns emerge, cells of circulation, some as large as Earth itself, rising and falling in a rhythm that's almost like breathing. The star breathes light. With each pulse of convection, with each cycle of rising heat and sinking coolness, the star maintains its balance. It's a delicate equilibrium, this dance between gravity trying to crush everything inward and the pressure of fusion pushing everything outward. Neither force wins. They simply hold each other, perfectly matched, for billions of years. There's a lesson in this, though the star doesn't teach it. It simply demonstrates, through its existence, what it means to be balanced, not through rigidity, but through constant, gentle adjustment. When one force pushes a little harder, the other responds. The star never fights itself. It flows, adapts, remains steady in the midst of enormous energies. On the surface, small bright regions appear and fade. Areas where magnetic fields have broken through, creating slightly hotter spots that glow more intensely. These are like freckles on the star's face, temporary marks that come and go. Some last for days, others for weeks. They drift across the surface as the star rotates, appearing on one side, traveling across the face, disappearing on the other side, only to emerge again when the rotation brings them back around. The star spins slowly, taking about 25 days to complete one rotation, much slower than Earth's daily spin. But then, the star is much larger, much more massive. There's no hurry. It has all the time in the world, and then some. Around the star, if planets have formed from that original disk of dust, they orbit in silence. The star's light falls on them constantly, a gift given without asking for anything in return. If there's a world in the right position, not too close, not too far, that light might warm oceans, drive weather, feed plants through the miracle of photosynthesis. Life might emerge, complex and beautiful, all of it powered by the star's patient burning. But the star knows nothing of this. It has no awareness of what its light creates. It simply shines, as a river simply flows, as wind simply blows. Purpose emerges not from intention, but from being what you are, fully and completely. Millions of years pass in silence. The star changes so slowly the change is almost invisible. In its core, hydrogen gradually depletes as it fuses into helium. But there's so much hydrogen, enough to power the fusion for 10 billion years, that this depletion is barely noticeable for the first few billion. It's like a lake so vast that even though water constantly flows out, the level seems never to drop. The light remains steady, warm, yellow-white, streaming out in all directions. If you could listen to the star, not with your ears, but with instruments that detect vibrations, you'd hear music. Stars ring like bells, their surfaces oscillating with complex patterns of sound waves trapped inside. These vibrations are too low for human ears, too slow, but they're there nonetheless. A deep hum, a cosmic chord sustained for eons. The star sings without knowing it sings. Around it, space is not entirely empty. Tiny particles stream outward from the surface. A stellar wind, gentle but constant, carrying atoms and energy out into the surrounding void. This wind is invisible, incredibly thin, but over time, it pushes against anything nearby, shaping the space around the star like breath-shaping mist on a cold morning. Some stars have companions, other stars orbiting nearby, the two locked in a gravitational dance. Our star might be alone, or it might have a partner, distant and dim. Either way, there's no loneliness in its existence. Loneliness requires the capacity to desire company. The star simply is, content in its being, whether solitary or partnered. Time continues its patient march forward. 1 billion years pass, then 2 billion. If you could watch the star across this entire span, you'd notice almost nothing different. The same glow, the same size, the same steady output of energy. This is the gift of the main sequence: stability, predictability, the comfort of knowing that today will be like yesterday, and tomorrow will be like today. On any planet circling the star, life might rise and fall, civilizations might bloom and fade, continents might drift, and mountains might erode to dust. But the star remains constant, the one reliable presence in a changing system, the anchor that holds everything in place. In its core, the fusion continues without pause, hydrogen to helium, mass converting to energy, Einstein's famous equation playing out trillions upon trillions of times each second. Every fusion releases a tiny burst of energy, a photon of light that begins its long journey toward the surface. The photons don't travel in straight lines. They bounce, absorbed by atoms and re-emitted in random directions, taking a zigzag path that might cover light years of distance, even though the star itself is less than 1 million miles across. A single photon might spend 100,000 years just trying to escape the star's interior, bumping into particles, changing direction, slowly working its way outward, like someone navigating a maze in the dark. But eventually, inevitably, the photon emerges. It breaks free from the surface and streams away at the speed of light, finally traveling in a straight line, carrying the warmth of fusion out into the cold universe. This is what starlight is: ancient energy, born in crushing pressure and heat, aged through 1,000 centuries of slow migration, finally released to travel freely across space. When you see starlight, you're seeing history. You're seeing the result of processes that began before your grandparents were born, perhaps before your species existed. The star doesn't know this. It has no concept of time passing, no memory of its youth, no anticipation of its future. It exists only in the eternal now, doing what stars do, being what stars are. Another 1 billion years slide by, soft as silk. 3 billion years into its life, the star remains much the same. If you could compare a photograph from the star's first 1 billion years to one from now, you'd struggle to spot the difference. Same brightness, same color, same gentle surface movements. The star has entered the deep middle of its life, the long, peaceful plateau where nothing much changes, where each day is like the one before. Think of a summer afternoon that stretches on forever, warm, golden, drowsy with contentment. That's the star's experience now, extended across eons. In the core, however, something is gradually shifting, though it will be billions of years more before the effects become visible. The hydrogen fuel, while still abundant, is slowly being consumed. As it fuses into helium, the helium sinks toward the center, being heavier than the hydrogen around it. A helium ash is building up in the very heart of the star, growing denser, growing larger, year by year, century by century. This ash doesn't burn, not yet. Helium requires much higher temperatures and pressures to fuse than hydrogen does. So, for now, it just accumulates, an inert core growing slowly at the star's center while the hydrogen fusion continues in a shell around it. But the star notices nothing. Its surface continues to shine with the same steady warmth. Out beyond the star, in the vast darkness of space, other stars are living their own lives. Some are younger, blazing blue-white with the fury of massive youth. Others are older, swollen into red giants, their cores heating up as they approach the end. And others still have already died, collapsed into white dwarfs, or exploded as supernovae, their material spreading back into the cosmic clouds from which new stars will one day form. The universe is full of stars at every stage of life, a garden of lights in different seasons, some budding, some blooming, some fading back into the earth. Our star is one among hundreds of billions in its galaxy alone, and there are hundreds of billions of galaxies, each with their own countless stars. It's a multitude beyond comprehension, yet each star is unique, living its own quiet journey from cloud to light to silence. Our star continues to rotate, continues to shine. On its surface, the convection cells rise and fall with patient regularity. Bright spots appear, drift, and fade. Occasionally, magnetic field lines tangle and snap, releasing bursts of energy in small flares, brief brightenings that last for hours or days before subsiding back to normal. These flares are gentle in our star. In larger, more massive stars, flares can be violent, dangerous. But our star is medium-sized, calm by nature. Its flares are like small sighs, brief expressions of energy that don't disturb the overall peace. If planets orbit the star, these flares might create auroras in their atmospheres, shimmering curtains of light dancing near the poles, green and blue and red, as charged particles from the star interact with magnetic fields and air. Beautiful side effects of the star's breathing. The stellar wind continues to flow outward, thin but persistent. It carries with it the star's magnetic field, stretching it out into space like invisible threads connecting the star to the farthest reaches of its influence. This magnetic field shapes the space around the star, deflecting incoming cosmic rays, creating a bubble of relative calm in the chaos of interstellar space. Within this bubble, called the heliosphere, conditions are quieter, more stable. Any planets benefit from this protection, shielded from much of the dangerous radiation that pervades the galaxy. The star, without knowing it, creates a safe haven simply by existing, simply by being what it is. 4 billion years now since birth. The star has reached middle age, though it shows no signs of aging. In human terms, this would be like reaching your 40s or 50s and still feeling exactly as you did in your 20s, strong, energetic, unchanging. The star has lost none of its brightness, none of its power. The fuel reserves are still enormous. In the core, the temperature has risen very slightly, not enough to notice from outside, but enough to speed up the fusion reactions just a tiny bit. This is the star's way of compensating for the growing helium core. As the core contracts under its own weight, it heats up, and the hotter it gets, the faster the surrounding hydrogen burns. It's a subtle feedback mechanism, the star regulating itself automatically, maintaining balance without conscious effort. Like your body maintaining its temperature without you having to think about it, the star adjusts, compensates, stays steady. 5 billion years arrive, quiet as dawn. If our star is similar to the sun, and let's imagine it is, it's now about halfway through its main sequence lifetime. Half of its hydrogen fuel has been consumed, half remains. The star stands at the midpoint of its peaceful existence, with as much time ahead as behind. There's something poignant in this, though the star feels nothing. To be halfway through a journey, to have come so far and still have so far to go. But the star doesn't measure its life in fractions or percentages. It simply continues, one fusion at a time, 1 second flowing into the next, being present in the only moment that exists. Now, the light streaming from its surface has traveled to distant corners of the galaxy. Some of those photons, launched from the star billions of years ago, are just now arriving at far-off worlds, their journey across space finally complete. They might fall on barren rocks, or ice, or perhaps on planets where beings look up and see our star as one small point among many in their night sky. Our star, in turn, is bathed in light from countless other stars, light that left those distant suns millions or billions of years ago, crossing the incomprehensible distances of space to finally arrive here. Stars exchange light like silent messages, though there's no message to convey, no meaning to extract, just light, pure and simple, the fundamental currency of the universe. The star continues its slow rotation day after day, year after year. From a distance, it looks like a perfect sphere, but if you could examine it closely, you'd see it slightly flattened at the poles, bulging gently at the equator due to its spin. This bulge is tiny. The star is 99.9% spherical, but it's there, a small imperfection that makes the star real rather than an idealized mathematical object. Imperfection is part of existence. Even stars aren't perfect spheres, aren't perfectly steady in their output, aren't uniform in composition or temperature. They're real, complex, textured, and somehow that makes them more beautiful, not less. 6 billion years have passed now since that first gathering of dust in the dark nebula. The star shines on, patient and bright, warming whatever worlds might circle it, contributing its light to the galaxy's soft glow. It asks for nothing, expects nothing, regrets nothing. It simply is, and in that simple being, it accomplishes everything a star is meant to accomplish. The star continues through its middle years with the same steady grace. 7 billion years have passed since its birth, and to an outside observer, it would still appear much the same as it did a billion years ago. A yellow-white sphere of light, constant and reliable, neither growing nor shrinking, neither brightening nor dimming in any noticeable way. But inside, deep in the core, the helium ash continues to build. The region where hydrogen can no longer fuse is growing larger, denser, hotter from gravitational compression. This inert core, is now about a quarter of the star's total mass, and it's beginning to affect the star's structure in subtle ways. The hydrogen shell around the helium core is fusing a bit faster now, producing slightly more energy than before. To compensate for this increased output, the star's outer layers have begun to expand very, very slowly, so slowly that the change is imperceptible over millions of years. The star is growing, but gently, like a flower opening over the course of a summer. If the star has planets, their climates might be warming degree by degree across geological timescales. Ice might be melting at the poles, seas might be rising, weather patterns shifting. But these changes happen so gradually that life, if it exists, has time to adapt, to migrate, to evolve in response. The star itself remains serene, unaware of any effects its slow changes might be causing. It simply responds to the physics governing its interior, adjusting its structure as conditions change, always seeking balance between the inward crush of gravity and the outward push of energy. 8 billion years arrive quietly, as all moments do in the star's existence. The star is now in its later middle age. If its total main sequence lifetime is about 10 billion years, it has perhaps 2 billion left before significant changes begin. But these numbers are estimates, approximations. The star doesn't count years. It has no awareness of time passing, no sense of approaching endings. It exists only in the present, burning hydrogen, producing light, being what it is. The surface temperature remains relatively stable, though careful measurements would reveal it's slightly warmer than it was a billion years ago. The star's color might have shifted very subtly toward the blue end of the spectrum, though to the naked eye it would still appear the same yellowish white it's always been. The convection on the surface continues, hot plasma rising, cooling, sinking, rising again in an endless cycle. These convection cells are the visible expression of the star's inner workings. The way the enormous energy generated in the core makes itself known at the surface. Watching these movements is hypnotic, like watching waves on the ocean or flames in a fire, patterns that never exactly repeat, order emerging from chaos, beauty from physics. Occasionally, larger events occur on the surface. A particularly strong magnetic field line might emerge from the interior, creating a sunspot, a region cooler than the surrounding surface, appearing dark by contrast, though still unimaginably hot by human standards. These spots can be larger than entire planets, vast magnetic structures that persist for weeks or months before dissolving back into the general flow. Around these sunspots, activity increases. Small flares become more common, bursts of light and energy, as magnetic field lines reconnect and release their stored energy. Particles are accelerated to high speeds, streaming away from the star, adding to the stellar wind. If planets orbit nearby, their upper atmospheres might glow more brightly during these events, lit up by the incoming energy. But even during these more active periods, the star remains fundamentally calm. It's not a violent star, not prone to dramatic outbursts. Its flares are gentle compared to those of larger, more massive stars. It shines with steady warmth, occasionally flickering brighter for a moment, then returning to its baseline glow. The stellar wind carries material away constantly: hydrogen, helium, and traces of heavier elements forged in the core or brought up from deeper layers. This wind is incredibly thin, barely there at all, but over billions of years it adds up. The star is very, very slowly losing mass, shedding tiny amounts of itself into space. This lost material drifts outward, cooling as it goes, eventually joining the interstellar medium, the thin gas and dust that fills the space between stars. One day, far in the future, this material might be gathered up in a new nebula, compressed by gravity, and incorporated into a new star. The universe recycles, nothing truly lost, everything transformed and used again. 9 billion years have now elapsed since the star's formation. The star is approaching the end of its main sequence lifetime. The helium core has grown large and dense, now making up about half the star's total mass. The hydrogen fusion is confined to a thin shell around this core, burning more intensely than ever before, trying to support the weight of the star's outer layers. The star has grown noticeably larger now, perhaps 50% bigger in diameter than it was in its youth, though still far from the enormous size it will eventually reach. Its brightness has increased too, by about 20 or 30%. If planets have been orbiting in the habitable zone, the region where liquid water can exist, they're getting warmer now, approaching the limits of habitability. But this is still a gradual process, unfolding over hundreds of millions of years. There's no sudden catastrophe, no dramatic shift, just slow, patient change, the star responding to the inexorable depletion of its fuel supply. The color of the star is shifting subtly. Where it once was a pure yellow-white, it's beginning to take on a very faint orange tinge, the first hint of the red it will eventually become. This color change is so gradual that it would be imperceptible to anyone watching in real time, but comparison across millions of years would reveal the trend. Inside the core, the helium sits inert, waiting. The temperature there is approaching 100 million degrees, but that's not quite hot enough yet to ignite helium fusion. That requires temperatures closer to 200 million degrees, and the core hasn't reached that threshold. So the helium just accumulates, growing denser and hotter from compression, patient in its own way, waiting for the moment when it too will burn. The star continues to rotate, continues to shine. Its magnetic field flips polarity every few decades or centuries, north becoming south, south becoming north, in cycles that have repeated throughout its life. These flips don't affect the star's overall behavior, just the orientation of its magnetic field, like a compass needle slowly rotating. 10 billion years arrive like all the years before, quietly, without fanfare. The star has now exhausted most of the hydrogen in its core. Only a thin shell around the helium core continues to fuse hydrogen into helium, and this shell is burning intensely, furiously, trying to maintain the pressure needed to support the star's outer layers against gravity's inward pull. The balance is shifting. For 10 billion years, the star has maintained equilibrium between gravity and pressure, between collapse and explosion. But that equilibrium is becoming harder to maintain. The star is beginning to struggle, though it knows nothing of struggle. It simply responds to conditions, adjusting as it has always adjusted, seeking stability even as stability becomes more difficult to achieve. The changes come slowly at first, then faster, though faster in a star's life still means millions of years. With most of the core's hydrogen exhausted, the fusion shell around the helium center burns hotter and hotter, producing more energy than the star did in its youth. This excess energy pushes the outer layers outward, and the star begins to swell in earnest now. Over the course of a few 100 million years, the star grows from its previous size to twice as large, then 3 times, then 5 times its original diameter. The surface is moving away from the core, expanding like a balloon being slowly inflated. And as the surface expands, it cools. The same amount of energy spread over a larger area produces less heat per square inch. The star's color shifts from yellow-white to orange, then to red. It's becoming a red giant, entering the final phase of its long existence. There's something both beautiful and melancholic about this transformation, though the star experiences neither beauty nor melancholy. It simply changes as all things change, following the path laid out by physics and the laws of stellar evolution. The same processes that gave it birth now guide it toward its ending. The outer layers expand further and further. The star grows to 10 times its original size, then 20, then 50 times larger. If it were our sun and Earth orbited at its current distance, the expanding star would eventually engulf Mercury's orbit, then Venus's orbit, the red surface coming closer and closer to Earth itself. But this happens over such vast timescales that there's nothing sudden about it. The star expands over millions of years, giving any planets time to adjust, to lose their atmospheres, to become scorched and barren as the star's increased brightness and proximity transform them. The star's luminosity increases dramatically, not because it's hotter, but because it's so much larger. More surface area means more light, even if each part of the surface is cooler than it used to be. The star might now be 100 or even 1,000 times brighter than it was in its youth, a vast red lantern glowing in space. From a distance, it's beautiful. The deep red glow is softer than the harsh white of younger stars, more gentle on the eyes, warm and ember-like. If you could see it from afar, it would look peaceful, serene, like sunset light made eternal. But up close, the reality is more complex. The surface is turbulent now, with enormous convection cells rising and falling, each one larger than the star's original diameter. Material from deep inside is being brought to the surface, then sinking back down in slow, massive flows. The star is churning, mixing itself, bringing up elements from the interior that have never seen the surface before. These elements change the star's composition slightly. Small amounts of carbon, nitrogen, and oxygen created in the core through fusion are now visible in the star's spectrum. The star is revealing its inner workings, displaying the products of billions of years of nuclear burning. The stellar wind increases in strength. Material is now streaming away from the star more rapidly than before, the outer layers so loosely bound that they're easily lifted off and carried away. The star is shedding mass, losing itself into space, becoming lighter even as it grows larger. This wind carries the star's enriched material outward, dispersing it into the interstellar medium. Future generations of stars, forming from this enriched gas, will inherit these heavier elements, building planets with iron cores and silicon crusts, and oceans of water, all made possible by the patient fusion work of stars like this one. In the core, dramatic changes are underway. The helium center has contracted under its own weight, growing denser and hotter as no fusion supports it from within. The temperature climbs past 100 million degrees, then 150 million, approaching the threshold where helium can ignite. The hydrogen shell around the core continues to burn fiercely, adding more helium to the core, increasing the pressure and temperature. The star is building toward a critical moment, a transition that will mark a new phase in its life. And then, after perhaps 100 million years as a red giant, the core temperature reaches 200 million degrees. Helium fusion ignites. This happens suddenly, not over millions of years, but in a matter of hours or days. The helium, compressed and heated beyond its capacity to resist, begins fusing into carbon. 3 helium nuclei combine to form one carbon nucleus, releasing energy in the process. The reaction is explosive at first, a helium flash that briefly outshines all the other processes in the star. But this flash is confined to the core, hidden deep inside. From the outside, the star shows no dramatic change. The surface doesn't explode or brighten suddenly. The helium flash is an internal event, invisible to external observers, like a change of heart that shows no sign on the face. The flash lasts only a few minutes, but in those minutes, the core releases more energy than the entire star normally produces. The energy heats the core, expands it slightly, and reduces the pressure. The runaway fusion reaction stabilizes, settling into a steady burn. Helium is now fusing into carbon at a sustainable rate, providing support from the core for the first time in millions of years. The star stabilizes somewhat. It stops expanding, might even shrink a bit. The outer layers settle into a new equilibrium, supported now by both the hydrogen shell burning around the core and the helium burning in the core itself. The star has found a second balance, a new stability, temporary but real. For a while, perhaps 100 million years, the star burns both hydrogen and helium, maintaining its red giant form, but no longer growing. It shines with a deep red glow, enormous and bright, an elder star in the later stages of its life. In the core, carbon accumulates from the helium fusion, just as helium accumulated from the hydrogen fusion before. The carbon sinks to the center, forming a new inert core, while helium continues to fuse in a shell around it, and hydrogen continues to fuse in an outer shell around that. The star now has a layered structure: carbon core, helium-burning shell, hydrogen-burning shell, and vast extended envelope. This is a complex, delicate balance. The star is juggling multiple processes, maintaining itself through increasingly intricate mechanisms. It's like an old tree, still alive and growing, but requiring more effort to draw water up from the roots, more care to maintain its structure. The stellar wind grows stronger still. The star is losing mass at an increasing rate, the outer layers being gently blown away by the pressure of light and the heat from below. Long streamers of gas extend from the star's poles, visible in certain wavelengths, like hair floating in water. The star continues in this state for a time, burning helium in its core, hydrogen in a shell, its enormous red envelope glowing softly in the darkness. But the helium, like the hydrogen before it, is finite. The fusion in the core continues, steadily converting helium into carbon, and the carbon core grows larger, denser, hotter. The star has perhaps 50 to 100 million years left in this phase, depending on its exact mass and composition. It's in the final chapter now, the closing pages of a story that began 10 billion years ago in a cloud of dust. There's a quietness to this ending, despite the enormous energies involved. The star isn't fighting its fate, isn't resisting the inevitable. It simply continues to burn what fuel remains, to shine as brightly as it can, to be a star, until being a star is no longer possible. The surface grows more turbulent. Huge pulsations begin, the star swelling larger, then contracting, then swelling again, in cycles that last months or years. These pulsations are the visible signs of instability in the interior, the star's structure responding to changes in the fusion rates and the pressure balance. During these pulsations, the star's brightness varies. At maximum size, it's cooler and dimmer. At minimum size, it's hotter and brighter. The star becomes a variable star, its light rising and falling in a regular rhythm, like slow breathing. If you could watch from a safe distance, you'd see this enormous red sphere growing and shrinking, glowing brighter and darker, pulsing like a heart. It's mesmerizing, this dance of light and size, order emerging from the complex physics of the stellar interior. The stellar wind increases during the pulsations, especially when the star is at its largest. Material is lifted off the surface, carried away, lost into space. The star is shedding its outer layers more rapidly now, creating a cloud of gas around itself, a glowing nebula lit by the star's light. This process continues for millions of years. Pulsate, shed material, pulsate again, shed more. The star is slowly unveiling itself, removing the outer layers to reveal the hot core within. It's like an onion being peeled, layer by layer, each layer drifting away as a shell of gas. In the core, the helium fusion is nearing its end. Most of the helium has been converted to carbon, with some oxygen mixed in from more complex fusion reactions. The carbon-oxygen core is now too cool to fuse. Carbon fusion requires temperatures of over 500 million degrees, and the star isn't massive enough to reach that. So, the core sits inert once more, contracting under gravity, heating from compression, but unable to ignite. The helium fusion continues in a thin shell around the core, burning the last reserves of helium. Above that, the hydrogen fusion continues in an even thinner shell. The star is burning on two fronts now, trying to support itself with fusion happening in shells, while the core itself sits dead. This cannot last. The shells burn through their fuel in a final burst of energy. The star pulsates more violently, shedding material faster. The outer envelope is almost entirely lost now, blown away into space, leaving only the hot core and a thin remaining layer of atmosphere. And then, over a period of just a few thousand years, a blink of an eye in stellar terms, the last of the envelope is shed. The outer layers drift away as a planetary nebula, a glowing shell of gas expanding into space, while at the center, the core is finally revealed. What remains is a white dwarf, a sphere about the size of Earth, but containing roughly half the star's original mass. It's made primarily of carbon and oxygen, compressed to incredible densities, with a thin atmosphere of hydrogen and helium on top. It glows white-hot from residual heat, over 100,000 degrees at the surface. Bright but tiny. The star's active life is over. It will never fuse elements again, never generate energy from nuclear reactions, never shine from internal fire. It is now simply a cooling ember, living off stored heat, fading slowly into darkness. But this fading will take a very long time. The white dwarf cools, but slowly, so slowly. With no internal energy generation and no way to cool except by radiating heat into space, the white dwarf might stay hot for billions of years. It begins as a blue-white point of light, intensely bright for its size. Then over eons it cools to yellow, to orange, to red, growing dimmer and dimmer. There's a profound peace in this final state. The white dwarf doesn't pulsate, doesn't shed material, doesn't change except to cool. It simply sits in space, radiating its remaining heat, a monument to the star it once was. The planetary nebula around it expands outward at thousands of miles per second, a glowing shell growing larger and larger. From Earth, if this were a nearby star, the nebula would appear as a beautiful ring or bubble, glowing in different colors as different elements fluoresce in the star's ultraviolet light. These nebulae are some of the most beautiful objects in the night sky, delicate, symmetrical, colorful. But they don't last forever. Over tens of thousands of years, the nebula spreads out, thins, merges with the interstellar medium. Eventually it becomes invisible, its material dispersed so widely that it's indistinguishable from the general gas between the stars. But that material is enriched now, containing carbon, nitrogen, oxygen, and other elements created in this star's interior and brought to the surface in its red giant phase. This enriched gas will one day be part of a new nebula, a new star-forming region. The next generation of stars will inherit this material, and planets forming around those stars will be made partly from the atoms forged in our star's core. In this way, the star continues not as light, but as substance, scattered and transformed, but never destroyed. The white dwarf continues to cool in silence. After 1 billion years, it has faded to a dim red glow, still visible, but weak. After 5 billion years, it's cooler still, barely emitting any light at all. After 10 billion years, roughly as long as the stars spent on the main sequence, the white dwarf has cooled to the point where it no longer glows visibly. It has become a black dwarf, a lump of crystallized carbon and oxygen, cold and dark, supported against gravity, not by heat or pressure, but by quantum mechanical effects. This is the final state, a cold, dark sphere, Earth-sized, silent, invisible except for the gravitational pull it still exerts on anything nearby. If planets still orbit, they circle this dark remnant, frozen and lifeless, receiving no warmth, no light. The star's journey is complete. From diffuse cloud to brilliant light, to cooling ember, to cold darkness, the cycle is finished. The star has returned to silence, to the quiet it emerged from billions of years ago. Now, the universe enters a phase so slow that even geological time seems hurried by comparison. The black dwarf sits in space, cold and dark, a monument made of carbon and oxygen, compressed to a density beyond earthly comprehension. In a teaspoon of this material, you could fit a ton of mass, the atoms packed so tightly that only quantum mechanics prevents further collapse. It doesn't shine. It emits no light, no heat beyond the faint infrared glow of an object barely warmer than the cosmic background. If you could stand on its surface, protected somehow from the enormous gravity, you would see nothing. No glow from the dwarf itself, only the light of other stars scattered across the sky, slowly shifting positions over millions of years as they orbit the galaxy. The black dwarf is essentially unchanging now. It will remain like this for timescales that dwarf the lifetime the star spent shining. Tens of billions of years pass, then 100 billion, then 1 trillion. The universe ages around it, evolving in ways the star cannot witness. Other stars are born, live their lives and die. Galaxies merge, their shapes transforming over billions of years. The universe continues to expand, the space between galaxies growing larger, the light from distant galaxies shifting redder and redder as they recede. But the black dwarf simply persists, patient as always, cooling so slowly that the change is almost theoretical. After 1 trillion years, it might have cooled by a few degrees. After 10 trillion years, a few degrees more. It asymptotically approaches absolute zero, never quite reaching it. The cooling curve flattening out across time periods longer than the current age of the universe. In the crystalline interior, the carbon and oxygen atoms are arranged in a perfect lattice, each atom held in place by the pressure and quantum effects. It's essentially a giant diamond, Earth-sized, dark and cold, floating in the void. If you could see it up close, it would look like smooth black glass, perfectly spherical, reflecting the faint light of distant stars. Nothing happens on the surface, no weather, no erosion, no change of any kind. The black dwarf is frozen in its final state, too cold for chemical reactions, too stable for radioactive decay to matter, too small for further collapse. It exists in a state of near-perfect stillness. If planets still orbit, unlikely after the turbulence of the red giant phase, but possible, they too are frozen, their surfaces cold enough that even gases like nitrogen and oxygen have frozen solid. These worlds orbit in darkness, receiving only the faint light of distant stars, their surfaces unchanged for billions upon billions of years. The black dwarf's gravity keeps them in orbit. The same force that once held the star together, now simply maintaining these orbits, not creating or destroying anything, just preserving the arrangement. Time continues its patient march. The universe reaches ages that are difficult to conceptualize. Quadrillions of years, quintillions. New stars have long since stopped forming in most galaxies. The universe has entered its underscore, quote, underscore 2 underscore, where most stars have burned out, and the night sky is filled more with black dwarfs, neutron stars, and black holes than with living, shining stars. The galaxy itself is dissolving. Over these enormous timescales, stars are occasionally ejected from the galaxy through gravitational interactions, flung out into intergalactic space to wander alone. Our black dwarf might be one of these ejected objects, now traveling through the vast darkness between galaxies, with no other stars nearby, no reference points except the distant, fading galaxies scattered across the sky. Or it might remain in what's left of the galaxy, part of a loose association of dead stars, black holes, and planets, all orbiting a central supermassive black hole that has grown by consuming much of the galaxy's original matter. Either way, the black dwarf continues unchanged and unchanging. In these late eras of the universe, even matter itself begins to face questions of stability. Some theories suggest that after timescales of 10 to the power of 35 years or more, protons might decay, their stability not perfect, but merely extraordinarily long-lived. If this is true, then eventually, over unimaginable ages, even the black dwarf would begin to slowly dissolve, its carbon and oxygen nuclei decaying into lighter particles, the solid sphere evaporating atom by atom. This process would take so long that it makes the star's main sequence lifetime seem like a brief flash. But in the end, if we wait long enough, the black dwarf might fade away entirely, transformed into a cloud of electrons, positrons, neutrinos, and photons dispersing into the void. Or perhaps protons are truly stable, and the black dwarf will persist forever, growing colder and colder, approaching but never reaching absolute zero, existing for eternity as a frozen remnant of a star that once shone brightly. Either way, the ending is the same: silence, stillness, the absence of change. The star has returned fully to the peace it came from, the same deep quiet that existed in the nebula before fusion first ignited, but now a quiet without the potential for awakening. There's something profound in this trajectory, from the dispersed to the gathered, from the cold to the hot, from darkness to light to darkness again. The star's existence describes an arc, a journey from one form of peace to another, with a long, brilliant period of shining in between. And in that shining, the star accomplished everything it needed to accomplish. It converted hydrogen into helium, helium into carbon and oxygen. It released light and heat into space. It potentially warmed planets, enabled life, allowed consciousness to emerge and look up at the stars and wonder about its origins. The atoms in your body, the carbon in your cells, the oxygen in your blood, the nitrogen in your DNA, were created in stars like this one, forged in the hot cores where fusion occurs, then scattered into space when the star died. You are made of stardust, quite literally the products of stellar fusion and stellar death. Every star that has ever lived and died has contributed to the enrichment of the universe, transforming simple hydrogen and helium into the complex chemistry that makes planets, oceans, and life possible. Our star is one among billions that have done this, will do this, are doing this now. And now, at the end of its journey, the star rests. It has given all it had to give: its light, its heat, its material, its time. What remains is simply the core, the compressed remnant, the monument to 10 billion years of fusion and light. Close your eyes now and imagine that silence. Imagine a sphere of dark crystal, Earth-sized, floating alone in a universe that has grown cold and empty. Imagine the stillness, the absolute absence of change, the peace that comes not from balance, but from completion, from having run the full course, from being finished. The star asked for nothing. It received nothing but dust and gravity, and from those simple ingredients, through the patient working of physics across billions of years, it created light, warmth, and the elements of life. It shone without knowing why, without expecting reward, without understanding its own beauty. And now it rests, silent and still, while around it the universe continues its own slow evolution toward equilibrium, toward the final state of maximum entropy, where all energy is evenly distributed and nothing more can happen. But that ending is still far away, almost infinitely far. For now the universe still has stars that shine, galaxies that spiral, life that grows and wonders and reaches toward understanding. The light from our star, launched billions of years ago, is still traveling outward, carrying the news of its existence to distant corners of space. And somewhere, perhaps, that light is falling on a world where someone looks up and sees it, one small point among many, and wonders about the star that created it, about the journey that light has traveled, about the patient burning that made it possible. The star would not know this, but if it could, perhaps it would be content, knowing that even in silence, even in darkness, its legacy continues, light still traveling, atoms still scattered, the universe slightly richer for its having existed. Rest now, quiet star, your work is done. The universe holds you gently in its vast embrace, honors you with eternal stillness, remembers you in the elements you created and the light you gave, from cloud to light to silence, from beginning to middle to end, from birth through life to peace. The journey is complete. But let us not leave our star just yet in that cold darkness. Let us linger a while longer in the vast stretches of time, watching what happens in the deep future, in ages so remote that they seem more like dreams than reality. The black dwarf drifts through space, silent and dark. Around it, the universe continues its slow transformation. Trillions of years pass, and the night sky changes in ways that would be unrecognizable to anyone who knew the earlier universe. Galaxies that once shone with billions of stars have gone dark, their stellar populations exhausted. The bright spiral arms have faded. The glowing nebulae where new stars once formed have long since dispersed. What remains are scattered remnants, black holes, neutron stars, white dwarfs, and black dwarfs, all slowly spreading apart as the universe's expansion continues. Our black dwarf might now be alone in a way that's hard to comprehend. The nearest other object, another dead star perhaps, or a wandering planet, might be light years away. The sky above is mostly empty, just a handful of distant points that might be other galaxies, all of them fading, receding, their light stretched so thin by expansion that they're barely visible. In this era, time itself seems to slow. With so little happening, with so few changes occurring, the passage of years becomes almost meaningless. 1 billion years might pass with nothing changing at all in the black dwarf's immediate vicinity. It simply exists, cold and still, a patient witness to the universe's long decline into darkness. The black dwarf's surface remains smooth, undisturbed. In the earlier universe, it might occasionally have been struck by a wandering asteroid or comet, creating a brief flash of heat, a small crater. But now, in this emptied cosmos, such collisions are extraordinarily rare. Space has become so vast and empty that objects almost never encounter each other. So the black dwarf sits in perfect stillness, its surface unmarked, its interior crystallized into a flawless lattice of carbon and oxygen atoms. If you could examine it atom by atom, you would find a structure of incredible precision, each atom in its proper place, the entire sphere one vast crystal. Deep in the quantum realm, however, something interesting happens. Even at temperatures near absolute zero, quantum effects ensure that atoms never quite stop moving entirely. They vibrate ever so slightly in what's called quantum zero-point motion. The black dwarf, though appearing perfectly still, is actually humming at the quantum level with these tiny vibrations. It's the universe's way of saying that perfect stillness is impossible, that even in the deepest cold and darkest silence, there remains a fundamental liveliness, an irreducible motion that can never be eliminated. The black dwarf hums its quiet quantum song, unheard by anyone, unchanging across timescales that make geological ages seem brief. More time passes, so much time that the numbers become meaningless. 10 to the power of 20 years, 10 to the power of 30 years, 10 to the power of 40 years. The universe is now incomprehensibly old, far older than it was when the star first formed. Most of the structures that existed in the early universe, galaxies, galaxy clusters, even large-scale cosmic structures, have been torn apart, by the accelerating expansion of space. The black dwarf exists now in what's called the black hole era of the universe's evolution. Most ordinary matter has either fallen into black holes or been ejected from gravitationally bound systems. The dominant objects in the universe are now black holes of various sizes, slowly evaporating through Hawking radiation, a quantum process that allows them to lose mass over time. This evaporation is incredibly slow. A solar mass black hole would take 10 to the power of 67 years to evaporate completely, a number so large it's almost impossible to grasp. Larger black holes take even longer, but given enough time, and time is the one thing the universe has in abundance, even these will eventually disappear. Our black dwarf might occasionally pass near one of these black holes, its orbit perturbed by the gravitational influence, or it might remain alone, far from any other object, drifting through the void in a straight line, never encountering anything again. The universe continues to cool. The cosmic background radiation, the afterglow of the Big Bang, once bright and hot, now cooled over the eons, has become unimaginably cold, just a tiny fraction of a degree above absolute zero. The black dwarf, having radiated away most of its heat, is now almost in thermal equilibrium with this background radiation, nearly the same temperature as the space around it. At this point, the black dwarf is as cold as it will ever get, not quite at absolute zero, but so close that the difference hardly matters. Its atoms still vibrate with quantum zero-point motion, but beyond that, there is no heat, no energy to speak of. Time continues. 10 to the power of 50 years, 10 to the power of 60 years. Numbers that have no meaning in human experience, that can barely be conceptualized even mathematically. And then, if the theories of proton decay are correct, something begins to happen. Very slowly, very rarely, individual protons in the black dwarf begin to decay. A proton transforms into lighter particles, a positron, a neutral pion, perhaps some neutrinos. The pion quickly decays further into photons. A tiny flash of light is released, so brief and faint it would be invisible even if anyone were there to see it. But there is no one to see. The universe is empty of observers, empty of life, empty of anything that could notice or care about this tiny event. Another proton decays, then another. The process is excruciatingly slow. An individual proton might have a half-life of 10 to the power of 35 years or more, but the black dwarf contains an enormous number of protons, and given enough time, they will all eventually decay. Over timescales of 10 to the power of 40 years or longer, the black dwarf slowly evaporates, atom by atom, proton by proton. Each decay releases a tiny bit of energy, a few photons that stream away into the darkness, never to return. The solid sphere gradually becomes less solid. Atoms disappear from the surface, then from the interior. The black dwarf shrinks, losing mass, its gravity weakening. What was once Earth-sized becomes smaller, moon-sized, then asteroid-sized, then boulder-sized. The process continues, patient and inexorable. The black dwarf is dissolving, returning to the void from which it came, though in a form completely different from the original nebula. Where it began as diffuse gas, it ends as a diffuse cloud of photons and leptons, the products of proton decay spreading out into space. Eventually, after perhaps 10 to the power of 100 years or more, the last proton decays. The last bit of matter that was once part of the star transforms into energy and particles. The black dwarf is gone, completely dissipated, nothing left but radiation spreading outward at the speed of light, growing thinner and thinner as it expands. The particles and photons that were once the black dwarf continue to spread through space, mixing with similar particles from countless other dead stars, all of them decayed, all of them returned to their simplest forms. The universe at this stage is filled with a thin soup of photons, neutrinos, electrons, and positrons, all at nearly the same temperature, all spread almost uniformly through the vastness of space. This is approaching what's called the, quote, fore of the universe, a state of maximum entropy where energy is distributed so evenly that no gradients exist, no differences in temperature or pressure, nothing to drive change or create structure. It's a state of perfect equilibrium, perfect uniformity, perfect stillness. In this era, time loses almost all meaning. With nothing changing, with no processes occurring, there's no way to mark the passage of time except by the pure counting of moments. 1 trillion years passes and nothing happens. Another trillion and still nothing. The universe exists in a state of frozen unchangingness that will persist, potentially, forever. The photons from our stars decay, if we can still call them our stars after all this transformation, continue to travel through space. They're redshifted now by the expansion of the universe, stretched to wavelengths longer than galaxies, their energy reduced to almost nothing. They're barely distinguishable from the cosmic background radiation, themselves becoming part of that all-pervading glow. These photons might travel forever, never encountering anything, never being absorbed or scattered, just propagating through the void at light speed, carrying the last infinitesimal remnant of the energy that was once generated in the star's core through fusion. Or perhaps, given infinite time, quantum effects might allow for rare and random events. In a universe at maximum entropy, thermal fluctuations can still occur, random concentrations of energy, brief departures from equilibrium that quickly dissipate. Over timescales of 10 to the power of 120 years or longer, it's theoretically possible for these fluctuations to become large enough to create structures, even complex structures. A random fluctuation might briefly collect some particles together, creating a temporary clump of matter before it disperses again. Given enough time, truly infinite time, fluctuations might even recreate something like a star, though the probability is so vanishingly small that it's essentially zero for any practical purpose. But in infinity, even the impossible becomes inevitable. So perhaps, in some unimaginably distant future, the particles that were once part of our star will randomly come together again, joining with other particles, forming a new structure. Not the same star, that particular arrangement is gone forever, but something new, something that carries forward the matter and energy in a different form. This is the universe's ultimate recycling program, operating on timescales that make the stellar life cycle seem instantaneous. Nothing is truly lost, just endlessly transformed, rearranged, dispersed, and occasionally regathered in the eternal dance of entropy and quantum fluctuation. Our star's journey, then, might not truly end even in the heat death. Its constituent parts persist, transformed beyond recognition, but still present, still part of the universe's total inventory of matter and energy. In a sense, the star becomes the universe itself, its particles mixing with all the other particles, its energy joining the universal background, indistinguishable and inseparable from the whole. There's something beautiful in this final dissolution. The way individual identity fades, but presence remains. The star loses its starness, but doesn't disappear. It just becomes everything, everywhere, part of the unified field of existence that the universe becomes in its final state. And in that state, there is peace, not the peace of stillness, for quantum fluctuations ensure that perfect stillness is impossible, but the peace of completion, of having run the full course from separation to union, from complexity to simplicity, from individual existence to merged existence with everything that is. The star began as separate particles coming together. It ends as separate particles moving apart. And in between was the beautiful complexity of stellar life, the fusion, the light, the warmth, the contribution to the cosmic evolution. Every stage was necessary. Every stage was perfect in its way. The gathering, the burning, the fading, the cooling, the decay, the dispersal, all part of one continuous process, one long journey from one form of unity to another. In the beginning, unity through undifferentiation, everything mixed together in the primordial nebula. In the end, unity through equilibrium, everything evenly distributed in the heat death. And in the middle, beautiful differentiation, stars and planets, light and dark, hot and cold, life and consciousness. Our star was part of that middle phase, that era of complexity and beauty. It played its role perfectly, creating the conditions for wonder, for awareness, for the universe to know itself through conscious observers. And now, having completed that role, it rests in the only form of rest that's ultimately possible: dissolution, back into the wholeness from which it came. But let us step back now from these unimaginable futures, these timescales beyond comprehension. Let us return to a more human perspective, a more graspable understanding. The star lived. It truly lived. For 10 billion years, it burned brightly, transforming matter into energy, creating light and warmth, synthesizing new elements, contributing to the enrichment of the universe. That life was real, meaningful, beautiful, even if no one was there to witness most of it. The star didn't need observers to validate its existence. It shone for its own sake. Or rather, it shone because shining is what stars do when conditions are right. There was no purpose beyond the shining itself, no goal beyond being what it was. And in that purposeless shining, purpose emerged. Planets might have formed, warmed by the star's light. Life might have arisen, fed by the star's energy. Consciousness might have developed, looked up at the star, and felt wonder. The star made all of this possible, not through intention, but through simple existence. This is the paradox of meaning in the universe. Nothing has inherent purpose, yet everything enables purpose to emerge. The star didn't try to create conditions for life, but by being a star, it did exactly that. Purpose arises not from design, but from possibility, from the simple fact that when energy flows and matter organizes, complexity emerges, and with complexity comes the potential for meaning. When the star finally faded and cooled, when its fusion ceased and its light went out, it had already accomplished everything a star can accomplish. It had no regrets, because regret requires consciousness. It had no sadness, because sadness requires awareness of loss. It simply transitioned from one state to another, as natural and inevitable as water flowing downhill. The atoms it created, the carbon and oxygen forged in its core, spread through space and became part of new systems. Some might be in your body right now, part of the molecules that make you who you are. When you breathe, when you think, when you feel, you're using atoms that might have been created in a star like this one, billions of years ago. In this way, the star lives on, not as itself, but as the building blocks of everything that came after. It gave its substance to the universe, enriching the cosmic chemistry, making complex molecules possible, enabling the emergence of planets, life, and consciousness. This is the star's true legacy, far more lasting than its light. The light traveled for a while, and then was absorbed, converted to heat, and radiated away. But the atoms persist, cycling through countless forms, stars, planets, living bodies, back to space, back to new stars. The material endures, transformed but never destroyed, eternal in its own way. So when we look up at the night sky and see the stars shining, we're seeing not just distant suns, but the ancestors of everything we are, the forges where our atoms were made, the sources of the light and energy that make life possible. Every star is a gift to the universe, giving light while it can, giving substance when it can no longer give light, contributing to the slow enrichment and complexification of the cosmos. Our star was one of billions that have made this contribution. Not special in that sense. It was a typical star, medium-sized, ordinary in almost every way. But precisely because it was typical, it represents the vast majority of stars, the patient workers of the universe who shine steadily for billions of years, asking nothing, giving everything. There's something deeply moving about the ordinary when you really look at it. The extraordinary captures our attention. Massive stars that explode as supernovae, black holes that warp space-time, exotic phenomena at the edges of physics. But the ordinary is what makes the universe work. The countless medium-sized stars burning steadily for billions of years, creating the stable conditions where complexity can emerge and persist. Our star was ordinary, and in its ordinariness, it was beautiful. It followed the same path that billions of stars have followed, are following, will follow. It demonstrated the elegance of physical law, the way simple rules applied consistently create patterns of incredible beauty and meaning, from dust to light to silence. This is the way of stars. And in that journey, they make everything else possible. They are the universe's way of creating complexity from simplicity, meaning from mechanism, beauty from physics. As our star rests now in its final stillness, whether as a cooling black dwarf in the near term or as dispersed particles in the deep future, it has earned that rest. It gave what it had to give. It completed its journey. It fulfilled its nature. And that, perhaps, is all any of us can do. Be what we are as fully and completely as possible, for as long as we're able. And then rest when rest comes, knowing that our substance persists, our contributions endure, and the universe is richer for our having been part of it. And so we reach the end of our journey together, following this single star from its quietest beginnings to its final, eternal rest. 10 billion years of light, 10 billion years of patient, steady burning. And then the long, slow fade into darkness, into silence, into peace. It's quite a story, isn't it? And yet, in many ways, it's the simplest story there is. A cloud of dust gathers, gravity pulls it together, heat builds, fusion ignites, light shines, fuel depletes, the light fades, silence returns. Nothing in this process required consciousness or intention. The star never decided to form, never chose to shine, never wanted to fade. It simply responded to the conditions around it, following the deep physical laws that govern all matter and energy in the universe. And yet, in that simple following of natural law, it created something beautiful, something essential, something that made everything else possible. When you really sit with this, it becomes almost overwhelming. Every atom of carbon in your body was created in a star's core, forged through fusion under temperatures and pressures beyond imagination, then scattered into space when that star died. The iron in your blood came from a supernova, a massive star's final explosive death. The oxygen you're breathing right now is made in stars, released into space, incorporated into clouds of gas, and eventually became part of Earth's atmosphere. You are made of stardust. This isn't poetry or metaphor. It's literal truth. The universe created stars, stars created elements, elements created planets, planets created conditions for life, and life eventually created you, a being capable of understanding this entire chain, capable of looking back at the stars and comprehending your own origin. The star we've been following might have contributed to this process. Its atoms might be part of you now, or part of the earth beneath you, or part of the air around you. There's no way to know for certain, but statistically, it's quite possible. You are connected to every star that has ever lived and died, linked by the atoms they created and scattered. And one day, those atoms will move on from you too. When you die, your body will decompose, and its atoms will return to the earth, or the air, or the water. They'll become part of other things, plants, animals, soil, stone. And billions of years from now, when our own sun swells into a red giant and eventually sheds its outer layers, those atoms might be carried back into space, dispersed into new clouds of gas, ready to be part of new stars, new planets, new possibilities. Nothing is ever truly lost. Everything is endlessly transformed. The universe recycles itself on the grandest scale imaginable, and we are all part of that cycling, that eternal transformation from one form to another. The star taught us this, though it never meant to teach anything. By simply being what it was, by following its natural course from beginning to end, it demonstrated the way all things work: the gathering, the peak, the decline, the return to rest, birth, life, death, and transformation. Not just for stars, but for galaxies, planets, mountains, rivers, forests, and yes, for us. There's something deeply comforting in understanding this pattern. It helps us see that endings aren't failures, they're completions. The star didn't fail when it ran out of fuel and faded. It succeeded. It completed its cycle. It gave everything it had to give, and then it rested, having accomplished exactly what a star is meant to accomplish. We can take comfort in this when we face our own endings, our own losses, our own fading of light. Everything that begins must end. Everything that shines must eventually grow dark. This isn't tragic, it's natural. It's the way things are meant to be. And in that ending, there's no annihilation, only transformation. The light fades, but the substance remains, ready to be part of something new. The star is at peace now. Whether you imagine it as a cooling white dwarf, slowly radiating its remaining heat into the void, or as a black dwarf in the distant future, cold and crystalline and still, or even as dispersed particles in the unimaginably remote future when protons themselves decay. In every version of its ending, there is peace. The struggle is over. The work is done. The fuel is spent. There's nothing left to do but rest, and so the star rests, held gently in the vast embrace of space-time, honored by the universe simply by being allowed to continue existing, even in silence, even in darkness. Can you feel that peace? Can you imagine it? Close your eyes and try to sense what the star might sense, if stars could sense anything: the absence of effort, the absence of burning, the absence of any need to be other than what you are, just existing quietly, completely, without struggle or resistance or desire. This is the peace that comes after a life fully lived. Not the peace of giving up or surrendering, but the peace of completion. The peace of having done what you came to do, having given what you had to give, having shown your light for as long as the fuel lasted. The star never questioned whether it was shining brightly enough. It never worried about running out of fuel. It never compared itself to other stars or felt inadequate because some stars burned brighter or lived longer. It simply was what it was, burning at exactly the rate its mass and composition allowed, being perfectly itself in every moment. There's profound wisdom in this, though again, the star doesn't know it's wise. It's just being natural, following its nature. But we, with our consciousness and our capacity for self-judgment and comparison, we can learn from this. What if we could be like the star? What if we could simply be ourselves, fully and completely, without comparison or judgment, giving what we have to give at whatever rate is natural for us, and then resting when the time for rest comes? The star never asked. Quote, 6. It simply was. And in simply being, it was perfect. It was exactly what the universe needed it to be, not a giant blue supergiant, not a tiny red dwarf, but a medium yellow star burning steadily for 10 billion years, contributing its light and its elements to the cosmic evolution. You are enough too, just as you are. You don't need to burn brighter than your nature allows. You don't need to last longer than your fuel permits. You just need to be yourself, as fully and authentically as possible, for as long as you're here. And then, when the time comes, you can rest, knowing you've completed your part of the pattern, your section of the great cosmic dance. The universe doesn't judge, it simply accepts. The star contributed what it could, and that was enough. When it had nothing left to give, the universe didn't reject it or cast it aside. It simply held the cooling ember gently, allowing it to rest, honoring it by allowing it to continue existing in whatever form it had become. You too will be held this way. When your light fades, when your energy depletes, when you can no longer do what you once did, the universe will not abandon you. You will be held gently in the same embrace that holds the star, the same fundamental acceptance that allows everything to be exactly what it is. There is no rush in the universe. The star took 10 million years just to form. It burned for 10 billion years. It will cool for trillions of years more. Everything happens at its own pace, in its own time. The universe is infinitely patient, never hurrying, never forcing, simply allowing each process to unfold at the rate that's natural for it. So, you don't need to rush either. You don't need to accomplish everything today, or this year, or even this lifetime. You're part of a process that extends across billions of years, across countless generations, across the entire history of the cosmos. Your contribution, whatever it is part of that larger pattern. It doesn't need to be huge or spectacular. It just needs to be yours. The star's contribution was light and atoms. Your contribution might be kindness or art, or simply the way you make someone feel when they're with you. Or it might be something you never even know about. A word you spoke that changed someone's life. A smile you gave that made someone's day. A choice you made that rippled out in ways you could never trace. Like the star, you might never know the full impact of your existence. The star didn't know if its light warmed planets or fed life. It just shone, and that was enough. You just need to live, to be present, to give what you can when you can, and that will be enough too. Now, let yourself settle even deeper into this moment. Feel your body against whatever surface is supporting you. Feel the gentle rhythm of your breathing, in and out, like the slow pulsations of a red giant star expanding and contracting, but so much faster, so much smaller, yet no less miraculous. Each breath brings in oxygen created in ancient stars. Each exhalation releases carbon dioxide, carbon that was forged in stellar cores billions of years ago. You are breathing stardust. With every breath, you participate in the same cycling of matter that the star participated in, the same endless transformation from one form to another. Feel the weight of your body pulled down by gravity, the same force that gathered the star's dust into a sphere, the same force that compressed its core until fusion ignited, the same force that holds you gently to this planet right now. Gravity connects you to the star, to the earth, to the moon, to the sun, to the entire cosmos. You are held by the same force that shapes galaxies. And feel the warmth of your body, generated by the chemical reactions in your cells, powered by the food you've eaten, which got its energy from the sun, which generates that energy through fusion, the same process that powered our star for 10 billion years. The warmth you feel right now is starlight, transformed and transferred, but ultimately the same energy that was born in stellar cores. You are star-warmed, star-made, star-connected. There is no separation between you and the cosmos. You are not in the universe. You are the universe, locally organized into the form you call yourself, temporarily gathered, eventually to be dispersed again, but always, always part of the whole. The star knew this without knowing it. It was never separate from the universe, never isolated or alone. It was always part of the great pattern, the cosmic dance, the endless flow of energy and matter through space and time. And so are you. So rest now in that knowledge. Let it sink deep into your awareness. You belong here. You are exactly where you're meant to be. Your existence is not an accident or a mistake. You are the universe's way of knowing itself, of experiencing itself, of being conscious of its own beauty and mystery. The star couldn't know itself, but you can know the star. And in knowing it, you know yourself, because you and the star are made of the same substance, governed by the same laws, part of the same story. Let your thoughts slow now, like the cooling of a white dwarf. Let them fade gently, like starlight dimming across billions of years. There's no need to think anymore, no need to figure anything out. Just be, like the star simply is. Just exist, quietly, peacefully, completely. Feel the darkness behind your closed eyelids. This is the same darkness that fills most of the universe, the gentle dark between stars, not empty, but full of potential, full of quantum fluctuations, full of the possibility of new light to come. Rest in that darkness. It's not frightening, it's peaceful. It's the natural state of things, the background from which all light emerges and to which all light returns. The darkness is home. The darkness is rest. The darkness is where the star sleeps now, content and complete. And you can sleep there too, safe and held, knowing that when you wake, you'll shine again, not for 10 billion years, perhaps, but for another day. And that's beautiful too. That's miracle enough. The star has shown us the way, from gathering to shining to fading to resting. Each phase perfect in its time, each transition natural and right. Nothing forced, nothing resisted, just the gentle unfolding of what is, moment by moment, breath by breath. So breathe now, slowly, deeply. Feel your body settling, relaxing, releasing the day's tensions. Let your shoulders drop. Let your jaw soften. Let your hands unfold and rest gently wherever they naturally fall. You have done enough today. You have shown your light. You have given what you had to give. Now is the time for rest, for restoration, for the gentle darkness that allows new light to be born. The star shines no more, but it remains. The light has faded, but the presence endures. And in that quiet persistence, there is dignity, beauty, completion. You too will remain, even when your particular light fades. The atoms that make you will continue. The effects of your existence will ripple forward. The love you've given will live in those who received it. Nothing is lost. Everything transforms. And in the end, everything returns to the peace from which it came. Sleep now, gentle one. Sleep like the star sleeps, deeply, completely, without worry or fear. The universe holds you. Time cradles you. Existence itself wraps around you like a soft blanket, warm and safe. You are stardust, resting after a long day of being human. Tomorrow, you'll gather yourself again, shine again, give again. But tonight, just rest. Just be still. Just be quiet. Just be. Like the star in its final silence, complete, content, at peace. Good night, beautiful light. Rest well. The universe loves you exactly as you are, and it will hold you gently forever. Sweet dreams, quiet star. Sweet dreams.